Okay, so we're going to talk about the mole-to-mole ratio. The mole-to-mole ratio is very simple, but it is the key in order to make all of stoichiometry work. Okay? What we're going to focus on here is the balanced chemical equation. The entire reason why we balance chemical equations is so we can get this mole-to-mole ratio. So that's the entire point of that whole last unit. We use the coefficients that we get from balancing a chemical equation to figure out the ratio of each substance in a chemical equation. In this way, we're actually able to look at a chemical equation, which remember represents a real chemical reaction, and we're able to start to compare amounts of the different substances, whether different reactants, different products, or a reactant and a product. When we do this ratio of coefficients, we're going to get them in units of moles. So again, you're seeing that mole concept show up as super vitally important for stoichiometry. So what does this actually look like? So example I is going to give us an unbalanced equation, and it wants us to actually find the molar ratios. So the very first thing I have to do is actually balance this equation. So what I like to do, again, is just draw my line right through that arrow, that yield sign. I'm going to list in the same order on both sides the elements that I see appearing in my chemical equation. I'm going to count them. And then I'm going to... Okay, so now that we have our equation balanced, we can move down here to the actual word problem. If 23.4 moles of barium oxide react, how many moles of carbon dioxide are required at STP? So we need to compare moles of barium oxide to moles of carbon dioxide. So that means we do need a molar ratio, okay? So we need to know how many moles of CO2 we get for every 1 mole of barium oxide. If we look up here, we have 1 mole CO2 for every 1 mole of barium oxide. So that's going to be our conversion factor. So I'm going to go ahead and set up my train tracks. 23.4 moles of barium oxide. Again, I want to cancel out moles of barium oxide, so that's what goes on the bottom. If I wanted to cancel out moles of carbon dioxide, this conversion factor would be flipped upside down. So if you ever are asked the other direction, you would do the same thing. You would just always, again, make sure whatever is on top right here gets canceled out on the bottom, and you're left with the units that you want to end with. So 23.4 times 1 divided by 1 gives me 23.4, and I'm left with moles of CO2. So our mole-to-mole ratio is enabling us to compare two different substances in the same balanced equation. All right, go ahead and pause and work on the two. Try on your own examples, and then when you are ready, unpause and we'll go over the answers. Okay, so for try on your own eye, this one just required us to balance our chemical equation and then to write the molar ratios. Notice here in the first one, we got an 8 over an 8, and we can simplify that down to 1 to 1. If you didn't simplify it down, it would still give you the right answer, but if you notice when you plug this in, it would just give you much bigger numbers. So if you can, simplify. Then our other two ratios were 8 over 1. Try on your own. J gives us another problem to balance. So we balance our chemical equation first, and we get our coefficients. I didn't write the one right here, but you always could if you wanted that reminder. Once you have your coefficients, you can use them to find the molar ratio and solve the problem. If you use 1 mole of nitrogen, how many moles of ammonia could be produced? So I'm putting my given in this very first spot. I want to cancel out moles of nitrogen, so I look up here and I have my 1 coefficient, 1 mole of nitrogen. My moles of nitrogen cancel out. I want to end up with moles of ammonia, so I need the coefficient from ammonia 2. So 2 moles of ammonia over 1 mole of nitrogen. 1 times 2 divided by 1 gives me 2 moles of ammonia.